So first, let's finish up our discussion on intermodal dispersion that we started in the last class. So we saw how in a step index fiber, basically the intermodal dispersion scales with this normalized index difference delta, right? Basically we saw roughly like for a typical multimode fiber, like the data rate is limited to about tens of megabit per second over a kilometer length scale, right? So the first improvement over this first generation of multimode fibers that was done was going to what are known as graded index fibers. Right, so as the name suggests, basically, as opposed to step index, which has like a constant refractive index in the core, and then there's a step change with a slightly lower refractive index in the cladding. Graded index has a smooth sort of graded refractive index profile. So, for example, if this is the fiber core here, radius A, then so basically the refractive index profile has some smooth variation across the core region like that. Right, so it's not a step function, but some smooth variation. So the maximum index is right in the middle, and then as the radial distance increases, the index goes down smoothly. So these are what are known as graded index fibers. So in general, we can write the refractive index profile for a graded index fiber, in terms of a power law like this. Okay, so in the core region, it's varying as some power of the radial distance here, right, where alpha is the power. And so if you put R equal to A, that's the cladding. So right, in the cladding, it's basically once it goes to the cladding, then the index is constant. Okay, so now you can imagine that for such a smoothly varying index profile, right? So let's imagine if we run an array at some angle here at the input, right? So in the step index fiber, because the index was constant, basically the ray path was straight lines. Right? But now the index is varying smoothly, so you can see that basically if we slice this up into very thin slices, right? At each interface, at each slice, basically we can think of the ray path as sort of, if you follow Snell's law, right? So the ray is going from a higher index to a lower index medium, so it will bend away from the normal. The normal points up, right? So it will keep bending away from the normal. So it will, you can imagine it will sort of curve like that. At some point, it will become parallel to the axis, right, to the longitudinal direction, and then it will like retrace its path back, right? So now it's going from lower index to higher index, and then it will bend sort of towards the normal. So anyway, it will just retrace the path, right? And you can keep following it like that. So one thing to notice is that so now the ray paths are curved, right? Not straight lines. Right, so for if you take this alpha tending to infinity, right, then basically, so for r less than alpha, this becomes 0. So then it's like a step index, right? But any lower finite values of alpha, you get this smooth variation, right? So, for general alpha graded index fiber, the ray paths are curved. And so how does this help with dispersion? Right, so the problem we saw in step index was, so if you imagine, for example, the shortest path is taken by the ray which is going straight through, right? Similarly, I mean, in this case also, like you can imagine an array which is going straight through along the axis, so it doesn't see any index state, so it just goes straight through. And then there were rays launched at other angles took longer paths. And in the step index case, all of these rays were traveling at the same speed because the index in the core was a constant n1, right? So the longer path rays took longer time, and that led to dispersion or pulse broadening. But here in the gradient index, what you can see is that, so obviously this curved, this one takes a longer path than the straight through. But what is also happening is that you can see as it goes away from the axis here, the index is lowering, right? And you know that the speed of light in the medium is c divided by the refractive index, right? So the refractive index is going down. So here it's traveling at higher speeds, right? So although it's taking a longer path, it's also traveling at higher speed, right? So if you think about the time taken, so it travels a longer distance also at a higher speed. So the relative time difference between these rays would be smaller, right, as compared to the step index, where the ray path was longer but the speed was the same. Okay, so that's sort of the idea, right? So again, if you recall, GOP students, in the fiber optics course, we discussed this in some detail, how to calculate the ray paths and the transit time, etc. So we won't go through all that in detail, but basically, you can sort of calculate, again, similar manner what we did for the step index, what is the minimum time taken for a ray, what is the maximum time taken for a ray, and then calculate the difference between them to estimate the broadening. Right? Of course, here you can see it will involve integrals and the computation will be a little bit more complex. But anyone can do that, and from this qualitative argument, you can already see that gradient index fibers would be better than step index, right? Because the rays traveling a longer path are also traveling faster. So, so this delta t, which is the difference between the ray time taken by the ray with the longest path and the shortest path, right? So it depends on alpha, of course, right? It depends on, so because the ray paths will depend on alpha. For certain alphas, you can solve. I mean, in general, for general alpha, you will probably need to solve this numerically. But for some certain alphas, you can obtain analytic solutions. Okay. So, for example, one interesting case that is useful is for alpha equal to 2 for a square law, right? So there you get this dispersion, which is the broadening per unit length. Like this. Okay. So recall in the step index fiber, we got something like n1 delta by c. Now here you are getting delta square. Okay. So how does this help us? Recall that delta was very small, right? So for optical fibers, delta is much smaller than 1. Right? For multimode fibers, we saw it was around 10 to the minus 2, right? So once you have delta square, right, it's a small number squared, so that's even smaller. So that's how it helps, right? So again, if we calculate like what is the limitation on the bit rate times the transmission distance, right? Again, bit rate is limited by 1 over delta t, right? So then that's inverse of this. Right, so again, if you put similar numbers, what we took for the step index. Right, so for the step index, we had, this limit was about 20 megabit per second kilometer. If you put the numbers here, you get this to be 16 gigabit per second kilometer. Okay, so you can see that we get an improvement by 2 to 3 orders of magnitude just because of these curved paths. So, and this alpha equal to 2 is also not only can be because we can get an analytic solution, also because it actually turns out this is sort of the optimum. Okay, so if you look at, if you calculate this dispersion delta T over L, so that's in nanosecond per kilometer, okay, as a function of alpha. So as a function of this exponent of the power law. Right, so for very high values of alpha, you approach the step index case. And so here, log scale on the y-axis. Okay, so it turns out that the optimum is around alpha equal to 2. Okay, and so recall for alpha tends to infinity for the step index case, this was approaching about 50. Right? So this was 50 nanosecond per kilometer. So this is for the same values here. You're just taking alpha. Right, so basically you can see that the dispersion sort of falls sharply right around alpha equal to 2. Okay, and this minimum is actually, again, people who've done the fiber optics course would recall this minimum occurs at alpha equal to 2 minus 2 delta, the exact minimum. But delta is anyway much smaller than 1, right? So this roughly occurs at alpha equal to 2. Right, and then it sharply rises as you go away from 2. Okay, so turns out that the optimum profile to minimize dispersion is also a square law profile. Right, so, and you can see that basically you can get orders of magnitude improvement. Equivalently, if you on this side plot sort of so if you plot this bit rate times the distance, so that's going up in the downward direction, right? Dispersion is going up in this direction. So higher dispersion means lower values of this bit rate times length. Right, so you can get sort of, you can see 3 orders of magnitude sort of improvement over a square law as opposed to a step index or any other kind of profile. Okay, so basically with this graded index fibers, sort of roughly in the 80s with the second generation of communication systems, people could extend the distances to like tens of kilometers at, let's say, 1 gigabit per second data rates. Right, but now again, as demands for data rate and traffic keeps increasing, so this was also not enough, right? So then one had to sort of go towards single mode fibers, where basically you eliminate this intermodal dispersion altogether, right? So again, recall basically this V number is what characterizes basically how many modes there are in the fiber, and if this V number is less than 2.0, 4, then you have a single mode fiber, right? So this depended on sort of the core size and this index difference, right? So people figured out how to make smaller core sizes and smaller index contrast, such that basically the fiber operated as single mode in this infrared range of wavelengths, or near infrared range of wavelengths, right? So then basically we eliminated this intermodal dispersion altogether, right? So now basically sort of there's only one ray, right? This ray picture works only in the multi-mode case where we can treat as different modes as different rays, right? But this is an approximate picture, you know. The exact picture is the wave picture. You solve for the Maxwell's equations, and for single mode, basically you just get one mode, right? So there is no question about different rays taking different paths or anything. There's only one mode. Right, so you can already imagine that would improve things quite a lot. But again, that's also not perfect. You haven't eliminated dispersion completely because there is still what is known as chromatic dispersion or group velocity dispersion that now determines your pulse broadening. So we'll take a look at that. And yeah, so for modern day systems, basically since sort of the 90s, extensively people moved to single mode fibers, and this is sort of the limiting dispersion mechanism. That's at least for long haul systems. Again, for shorter distance scales, as I said, like sort of below a kilometer, like within data servers or sort of small metro area network, people are still sort of looking at multi-mode fibers or graded index fibers. But for long haul systems, basically we moved exclusively to single mode fibers. Okay, so then basically the dispersion mechanism here is intramodal because there is only one mode. Chromatic because basically it comes from the spread in frequencies or different frequencies traveling at different speeds, or group velocity. Okay, so maybe just a few words on single mode fibers, right? So basically the conventional single mode fiber is a step index fiber, right? So you have some core radius A here, index N1 and N2, right? So typical, so the standard or conventional single mode fiber SMF, right? The core diameter here is about let's say 8 to 10 micron. Okay, and then you have a cladding diameter of about 125 micron. But anyway, that's immaterial because we sort of take the cladding to be infinite because this is big enough that the mode has decayed to 0, so it doesn't see the edge of the clad. Right, so again, recall this V number is right, or we can write it in terms of delta like this, N1 actually. Right, so this has to be less than right. So if you for a given fiber, right? So So A here is fixed for a given fiber. Also, this delta index difference is fixed, right? So typically, this is sort of few times, so like maybe like 3 times 10 to the minus 3 or something in this range. This delta. Okay, so and N1 and N2 are sort of around 1.45. So for a given fiber, right, the wavelength at which this V becomes this value is known as a cutoff wavelength, right? So V at the cutoff wavelength is equal to this, right? So for this conventional sort of standard single mode fiber, the cutoff wavelength typically is around 1.2 micron, right? So again, recall these telecom bands that we had went from sort of 1.25 to 1.65 micron, right? And we want the fiber to be single mode over that entire range, right? So the cutoff wavelength has to be smaller than that, right? So you can see here that for wavelengths longer than the cutoff wavelength, the V will be smaller than this. Right, so then for the telecom range of typical wavelengths that is used, so if we look at this range of wavelengths, then the V number is between, let's say, 2 and 2.4. Right, so and if you look at the fundamental mode, so if this is the core, so the fundamental mode profile looks like Gaussian in the radial direction, right? So it's a Gaussian field profile or intensity profile, and so again this is the core radius A, and there is a mode field spot size W, right? And this W over A. So basically, how much, in other words, how much the field is confined in the core, that's a function of this V number, right? And so basically, again, recall there are some empirical relations that one can use to find this in terms of the V number. Okay. So given a particular wavelength, you can find what the V number is, and you can calculate what the spot size of the mode is at that wavelength, right? Or equally to the confinement factor, how much power is confined in the core. So the spot size, of course, so decreases with increasing V number. Right, so it goes like that. So you can see that, so we operate, as I said, so here, right? So typically we are here. So you can see that W is sort of roughly equal to A or slightly smaller. So most of the mode is inside the core. Right? So as you decrease V number, then W increases, right? And the mode starts leaking out more into the clamp. So which is also bad, for example, for bending losses that we discussed a couple of classes, right? So this is sort of the region we work in, 2 to 2.4. Right, so fundamentally, where is this chromatic dispersion coming from? Because we can write this mode profile, right, as something like, so if we write the electric field profile, right? So as a function of position and time, so there is some polarization, right? So for example, again, recall that the fundamental mode here is the LP, so-called LP01 mode, right? So there are two degenerate polarizations, either field pointing in the x direction or y direction, right? And then some field profile, and then there's a propagation constant, which tells me how the phase is propagating with propagation, right? So this is analogous to the wave vector in free space. And then the frequency harmonic dependence, right? So this, we are looking at the mode at a particular frequency or a particular wavelength, right? So this mode profile, you know, again, for the LP0, for these LP modes, the exact mode profile are Bessel functions, right? But the lowest order LP01 mode, this mode profile can be well approximated by Gaussian, like that. Where W is this again mode, what size here? Right. So basically, and this beta, recall, is the solution to the wave equation, right? In this with this geometry and boundary conditions, right? So that beta propagation constant is a function of frequency, right? And so recall, we can write this as this 2 pi by lambda, which is the free space wave vector times an effective index, right? And this effective index lies between the core and cladding indices. Again, the more well confined a mode is, the closer n effective is to n1. Right? If it's leaking out into the cladding, then it's closer to it. Right, so basically, this n effective is a function of frequency or wavelength, which implies this propagation constant is also a function of frequency or wavelength, right? And you know, for this wave like this, right? So this looks like a plane wave, right? With e to the I omega t minus kz, it looks something like that, omega t minus beta z, right? So you know that the speed, so the group velocity is given by d omega by dt, right? And now if this is a function of frequency, then that group velocity will also be a function of frequency, right? Which means the group velocity being frequency dependent means if my signal that I am sending through the fiber, if it has different frequency components, all of them are traveling at different speeds, right? So at the input, I launch all of them together, but by the time they reach the receiver, all of them are arriving at different points in time, which leads to a broad. Right. So in the intermodal case, it was different spatial modes which were arriving at different times. Here, different frequency components within the same spatial mode are arriving at different times. Right. So recall this. I mean, for this step index kind of fiber, we could solve for the modes exactly, right? And one could get curves for this. So if you define a normalized propagation constant like this, right? So B lies between 0 and 1, right? Because n effective lies between n2 and n1. So you can see this B lies between 0 and 1. And so for a given fiber, right, for a given V number, basically one could solve for this B for the fundamental mode, right? So for example, you get curves like this, right? So this is V and this is V. So you can think of V as something like frequency or wavelength, right? because again, right? So V is for a given fiber, all these are fixed. So V just depends on inversely with wavelength or directly with frequency, right? And B is basically this solution to the wave equation or the propagation constant normalized. Right, so it lies between 0 and 1, and so this is for the fundamental LP01 mode for the single mode fiber. Okay, so basically this is the single mode region, right? 2.405 again, is cut off. So on this side, this is the single mode region. So the next mode sort of starts from here. This would be like LP11. Right, so for the telecom range of wavelengths, we are typically in this region here, again, between 2 and 2.4. Okay, so for that, the normalized this propagation constant lies between roughly like sort of 0.5 to 0.7 in that range. Okay, so one can get like a empirical formula for this VV curve also. So again, recall. So okay, so this works well for V numbers in this range, which is suitable for our telecom applications. Right? So for this single mode step index fiber, we can calculate for a given fiber, right? We know what the V number is. We can calculate what the propagation constant is at any particular wavelength or frequency. Right, so as we change for a given fiber, as we change the wavelength of frequency, this V number changes, so the propagation constant changes, right? So this beta changes. So that's why this is a function of frequency. Right, so if we look at the group velocity, yeah?
So what is small b?
So small b is just a normalized propagation constant, right? So the actual propagation constant you can see is this free space wave number k0 times this n effective. This small b is just a normalized way of defining this. So we just subtract n2 from n effective and divide by n1 minus n2. So you can see that because n effective lies between n1 and n2, the minimum value of b is 0 if n effective is n2, and the maximum value of b is 1 when n effective is 1. Right, so small b lies between 0 and 1. It's just a normalized way of writing the propagation constant. Yeah, just like V is also sometimes known as a normalized frequency, right? Because basically, so this is frequency, right? We've normalized it with sort of dimensions of the fiber, right? So this BV diagram, for example, you could have two different fibers, right? Such that their core size is different and then the index difference is different, but for some particular wavelengths, their V numbers could be in this range. So basically, what this is saying is that for a step index fiber, this curve is universal, right? So any given fiber, you just calculate the V number, you can get what the value of the propagation constant is, irrespective of the details of the individual fiber, right? So this could be any number, these difference, right? So one fiber could have this as 8 micron, another fiber could have a 10 micron, in one case, this index difference would be 10 to the minus 3. In another case, let's say it's 5 times 10 to the minus 3. Right? Whatever the case, as long as you have a step index fiber, the propagation constant just depends on the V number, not on the individual values. Basically, that's what it says. Right, so that's convenient because we don't need to. So we can use the same results for all the fibers that we are using just from the V number. Okay, so basically now if you look at the group velocity, right, so this is sort of like the propagation constant versus frequency, right? And you know, group velocity is sort of the derivative of the frequency with respect to the wave vector, right? D omega by dk or d omega by d beta. So you can basically think that the slope of this is giving you the group velocity, right? Of course, these are normalized numbers, but roughly you can think of the slope as giving you something proportional to the group velocity. And you can see that this is not a straight line or something, so the slope is actually varying, right? So as I change wavelength or frequency, the slope changes, which means I have a different group velocity. Right, so if you look at the group velocity, that's defined as the derivative like that, right? So I can write this as 1 over d beta by d omega because this is easier to compute, right? Because sort of we take the frequency as the independent variable under our control at the input, and then we see how the propagation constant varies with that. So we can also write this as, if you recall, C over Ng, right? Where Ng is, yeah, so this Ng is N effective right? So you can get this from if you put beta equal to omega over c times N effective here, right? And just compute this derivative. You can write this like this, you can check, wherein the group index is given by this effective index plus the derivative of the effective index with frequency. Right, so in general, this is also function of frequency, right? So these are functions of frequency, and this group index is also a function of frequency, so the group velocity is also a function of frequency. Right, so this is what chromatic or group velocity dispersion means. So now if you look at the propagation time through a length of fiber for the frequency component omega, right? So in a similar manner, what we did for intermodal, we sort of computed that this travel time for different modes or different rays. Here we compute the traveling time for different frequency components. So this is basically the length of the fiber divided by the group velocity, right? That's the time taken. So if we put this expression here, get that. Right, and now basically this is a function of frequency. So the this transit time is a function of frequency. So if you look at the broadening then, so delta t, I can compute as So take the derivative of this with, and then multiply by my pulse bandwidth. Right? So this gives me the frequency components present in my pulse or my signal. Right? And the broadening that I'll get is basically I'll take this derivative to see what is the difference in the speed between different or different in travel times between different frequency components and multiply by the bandwidth. Right, so for T, if you substitute this, you can see that so here I substitute so basically I get the second derivative of beta with respect to omega. Okay, so this is written as beta with a subscript 2 to denote the second derivative. Okay, so this beta 2 you can see is basically defined as the broadening divided per unit length per unit bandwidth. Right, so this is known as the GVD parameter or group velocity dispersion parameter. So the units you can see, so this is time, seconds, this is hertz or radian per second. So this is per second, so that goes above, so we get a second square in the numerator, and then we have a length in the denominator. So this has units of second square per meter. So typically for these optical fibers, you would see that the numbers are quoted in picosecond square per kilometer. Right, so picosecond is 10 to the minus 12 seconds. So this will be like 10 to the minus 24 second per into c meter. So that's sort of the scale of the dispersion that we are talking about. Okay. Right, so here you can see that, so in the intermodal case, basically this delta T over L was just some constant depending on the fiber parameters, right? But now here we have a quantity which sort of also is determined by the, so if you look at the broadening, right, that also depends on the bandwidth, right? So this beta 2 we will see depends on the fiber, right? So this will be some number corresponding to the fiber we are using, and so you can see that the broadening is scale with length, just like in the intermodal case also, but also with the bandwidth. So in the intermodal case, the bandwidth didn't come into the picture, right? Because we were just talking about spatial units. So this is basically in frequency units. As I said that many times in this area we use wavelength units. So we can do the same thing in wavelength units. Right, so again recall, like if you have some bandwidth in frequency space, right, equivalently I can look at that as the bandwidth in wavelength space, right, again by this relation of, right, so right, if we discussed sort of the couple of classes ago. Right, so equally we can define this broadening, right, as sort of instead of frequency, we say that the transit time for different wavelengths are different, right? and then we can look at in wavelength space like this. So right, so this T I can write as a function of wavelength again, where so L by Vg, where Vg is a function of wavelength, right? And where Vg I can write again as C over Ng, right? So in frequency it looks like this. So you can check that if you write in terms of wavelength, in wavelength there is a minus here instead of plus. Okay. Anyway, so but we can define this group index in wavelength units like this. So that comes here. Right. So again, when we take so if we put this expression for T in here, then basically delta T we can write as, so we put L over Vg here, so this becomes L times again delta lambda times the derivative of 1 over Vg with wavelength. Right, so I just put L over Vg here. So L is a constant, comes out, delta lambda is here, and then 1 over Vg we take the derivative with respect to wavelength. Right, so this one derivative of 1 over Vg with respect to wavelength, or sort of you can see this is basically 1 over C times the derivative of Ng with respect to wavelength. This is defined as parameter capital D, which is known as the dispersion parameter. Okay, this is basically the dispersion in wavelength units. So you can see D is basically delta T broadening per unit length per unit bandwidth in wavelength. Right, so this beta 2 was the broadening per unit length per unit frequency bandwidth. This D is basically same thing except now per unit wavelength bandwidth. Right, and so you can see basically obviously beta 2 and D are related, right? They are not independent because we've just done a change of variable. So you can check that the relation between D and beta 2 is given by this. Okay. Right. So recall. So this beta 2 is the second derivative of beta with respect to omega. Okay. And D is in wavelength. So basically, D is this, right? Or equivalently, 1 over C D over D lambda of Ng of lambda, right? Right, and we can use this expression for Ng of lambda. So you can see that this will come out to be the second derivative of the effective index with wavelength. Okay. So yeah, they're the same thing. Just you can see the difference by scaling because of change of units, and they depend on the second derivative of this, either the propagation constant or the effective index is basically related to the propagation constant. So the second derivative with frequency of it. Right, so the units of D, you can see, so this is second, length meter, and delta lambda, recall, is also units of length, right? Wavelength is units of length. So typically we talk about nanometer, right? So the typical units that you will see here, so delta T is measured in picosecond, delta lambda bandwidth in nanometer, and the length in kilometer. Okay, so the units of D typically you would see picosecond per nanometer per kilometer. Right? For beta 2 it was picosecond square per kilometer. So if you look at again this metric of the bit rate times the maximum link length over that bit rate can be maintained. So if we again say that the bit rate is limited, so the bit period has to be more than the pulse broadening. So the bit rate is limited to 1 over delta t. So if you put delta t equal to this, d times L times delta lambda, you can see that the maximum one can have is d times delta lambda. Right, so the maximum bit rate is inversely proportional to this dispersion parameter. Right, so for high data rates, we want a small dispersion parameter. So, sorry, so this is L. So bit rate times L is right. So we need a small dispersion parameter and also a small bandwidth for the source. One thing to note here is D and beta 2 have opposite signs. There's a minus here. So each of these beta 2 or D can be positive or negative, right? But it's not that if positive value gives you broadening, negative will give you compression, right? Because this is magnitude, so doesn't matter, right? Either both positive and negative values will give you broadening, right? The sign just tells you which frequency components will travel faster or slower, right? So you can see here. So for example, if D is positive, that means that 1 over Vg increases with wavelength, or equivalently Vg decreases with increasing wavelength if D is positive, right? Which means higher wavelengths travel slower for positive D, and for negative D, higher wavelengths travel faster. So in one case, like the lower frequency components will arrive first, and in the other case, the higher frequency components will arrive first, but in both cases, you will get broadening. Right? Assuming that you start from all frequency components starting together. So anyway, we'll look at some of this in more detail, what we mean by these different frequency components traveling at different speeds and what is the effect on the pulse, etc. But yeah, so just to give you some idea about some numbers here, again, if you look at a standard single mode fiber, this D, so you might have heard or know that this dispersion crosses 0 for these silica fibers at around 1.3 micron, right? So if you look at 1.3 micron wavelength, this value of D is very, very small, near 0, like 1 picosecond per nanometer kilometer at 1.3 micron. Okay, so let's say we use a semiconductor laser diode. which has a spectral bandwidth of about 1 nanometer. Okay, so if you put these numbers here, you'll see that. So this is not even stabilized laser. Okay, so-called like monochromatic or single frequency laser. This bandwidth is quite broad, right? So in frequency units, this is about 100 gigahertz at roughly 1.5 micron wavelength. Okay, so these are just simple laser diodes which are not stabilized using external cavities or whatnot. Nowadays, you can get actually single mode lasers where this delta lambda is much less than 1 picometer. Okay, so in tens of femtometer. So really almost single frequency. But anyway, even if you just put this sort of reasonable or like fairly high number by today's standards, the value that you get here is about 1 terabit per second kilometer. Okay, so you can see how much we've improved going from multi-mode fibers to single mode fibers, right? In multi-mode, we were talking about megabit per second, gigabit per second, like maybe tens of gigabit per second, but now here we moved to terabit per second. And these are with even not optimized numbers here. Just operating at close to the zero dispersion wavelength of glass with a reasonable laser diode. These are very cheap nowadays, like few dollars you can buy this laser diodes. But you can see already that you can do it way better. But again, by today's traffic demands, etc., we'll see further optimizations on this and how to boost this even further. Right. So in the beginning of the class, we discussed like nowadays we want to go to like tens of terabit per second over like hundreds of kilometers. Right. So, for example, you could modulate these laser diodes directly with current at like 2 gigabit per second. So that's the data rate you're putting on it. So then you can see from here you can go up to like 50 kilometers. I mean, so even if you use worse laser diodes with like 5 nanometer or 10 nanometer bandwidth, you can go up to like roughly 50 kilometers or 100 kilometers with these systems. Okay, so this was sort of roughly, I would say, like the third generation of optical communication systems, right? And then the fourth generation, we sort of started compensating even for this chromatic dispersion, and then sort of started using external electro-optic modulators to boost this, and also optical amplifiers and WDM systems. Right. So this you can see that basically this dispersion parameter is sort of how the group's velocity varies with frequency or wavelength. So in our optical fiber case, basically, as we also sort of briefly mentioned, it comes from sort of two, or there are two major sources for this dispersion. One is the material itself, right? So here we saw, for example, so here you can see that this parameter depends on the derivative of this index with wavelength, right? So, and this N effective we saw this lies between the coherent cladding index, right? So, for example, if the material index, refractive index depends on wavelength, which every material's refractive index depends on wavelength, right? Then basically you can see that there will be a dispersion from the material itself, right? And then the other contribution is we saw this BV curve, right? So this, for example, says that even if you have constant N1 and N2, right? So this V parameter dependent on this core size N1, N2, and the wavelength. So if we fixed N1, N2, basically saying that let's say there is no material dispersion, even then when we vary the wavelength, right, the V parameter changes, and we get a different propagation constant, and so basically the slope here is changing, right? So just from the waveguiding effect itself, there is a dependence of the group velocity on the frequency. So that is the waveguide contribution or the waveguide dispersion. Okay, so these are the two contributing factors, and we look at each of them individually, specifically for our single mode fibers made out of silica that are used in optical communication systems. So, okay, just one thing maybe to discuss. So recall, so D and beta 2 are opposite sides. Okay, so there is some terminology. So if D is less than 0, right, equivalently this means that beta 2 is greater than 0. So if D is negative and beta 2 is positive, this is known as normal dispersion. Okay, it's called normal because this is the sign of the dispersion. If you pick up any material at random and look at some particular wavelength range at random, typically you will find this sign. That's why it's called normal. Okay, the opposite sign, if D is positive and B is beta 2 is negative, this is known as anomalous dispersion. Again, for the same reason, anomalous means it's rarer. Typically, you find this case, not this case. Okay, again, so what does this mean? Normal means like, so recall this means that so D by D lambda of 1 over Vg is negative. This implies Vg increases with increasing lambda, right? So this means what? That higher wavelengths or lower frequencies, so we call them red, from sort of, if you look at the visible spectrum, red are higher wavelengths and blue are shorter wavelengths, right? So typically that terminology we can use in general for any, so in optical communication, although we are using near infrared wavelengths, so by red we mean higher wavelengths, right? So red travels faster, right? So, and in this case, this will be opposite. So Vg decreases with increasing wavelength. So this means that blue travels faster, or lower wavelengths travel faster. Right? So basically the sign and this terminology you will see in many places. Right, so again, it's not that in one case you will get broadening, in the other case you will get compression. Right? In general, in both cases you will get broadening. Right, and way to understand that is, so let's say I have some spread of frequencies or wavelength here. Right, so at the input, when I launch the wave, so if I look at the temporal pulse, I can sort of imagine that all the frequency components, so if I look at the different frequencies here, omega 1, omega 2, up to omega some n, right? So all of them are present for all the time together. Okay. So the power is sort of made up by some power is at frequency omega 1, some of it is omega 2, omega 3, okay, something like this. And then once you send it through the fiber, each of these frequency components are traveling at different speeds, right? So now if, let's say, you have normal dispersion, then the red or the lower frequency is traveling faster. So what will happen here at the output? So earlier lower times, omega lower frequency components will arrive first. Okay. So and this would lead to broadening, right? Make this broader. Right. So now the different frequency components have sort of split in time. Right. So in this case, for normal dispersion, the lower frequency arrives first, whereas in the anomalous case, you'll get the same broadening, except now the higher frequency will arrive first. Okay. Of course, if at the input you had a so-called chirp pulse, where all the frequency components are not present together, right? You can try to compensate the effect of this by, right? Like, so for example, here lower frequencies are arriving first. So if the input, if the lower frequencies were arriving after the higher frequencies, they will catch up through the fiber if you have normal dispersion, right? So in certain special cases where you have a pre-chirp pulse, where at the input itself your frequencies are not all present together at all time, but are already sort of split in time a little bit, then you can, by using the right type of dispersion, you can get the pulse to compress a little bit. Okay, so we'll discuss that mathematically in a bit more detail later. But yeah, just to so that you are aware of this terminology of normal dispersion, anomalous dispersion, etc. Right. So let's see how this contribution of material and waveguide comes in. So again, if you look at this normalized propagation constant, or normalized index, effective index. Right. So you can write this as delta, right? So recall delta is basically n1 minus n2 divided by either n1 or n2. Doesn't matter for delta much less than 1. So n1 and n2 are very close to each other, right? So for single mode fibers, for example, n1 would be 1.455 and n2 will be 1.450, something like that. Right? So this normalized index delta, we take the index difference and divide by either n1 or n2. We get basically the same value. Right. So this n1 minus n2, I can write it as n2 times delta. Right. So basically the effective index here. The actual effective index in terms of the normalized index, I can write like that. Right. So now recall this D parameter we saw was basically the second derivative of this effective index with respect to wavelength. Right. So we just put this expression for an effective here. Okay. So then we see we have two contributions. So first one here, you can see that just the variation of the index. This is the cladding index, right? This is just the silica refractive index, right? How that varies with wavelength. So this is known as the material dispersion. So basically N2 is basically the silica refractive index, how it varies with wavelength. Plus the second contribution here, right? So N2 and delta are, so in the second case here, if this is basically coming from the variation of this this parameter, the normalized index or the normalized propagation constant, how that varies with wavelength. Okay, so we can write this in terms of the BV curve, right? So again, we call this, we had this expression for this B as a function of V. Okay, so this thing we can write in terms of the V parameter like this. Okay, so here basically we do a change of variables. So we from wavelength we go to V. Okay, so recall V is proportional to, inversely proportional to wavelength. So we do this change of variables. So dV by d lambda is basically just minus V over lambda. Right, so you do this first for one differential and then do it again for the second differential, and so you'll see you get this. Right, so you can see here basically now it depends on the so B is a function of V, right? So you see that somehow, somewhere this depends on the slope of this BV curve, right? I mean, the second derivative. So this is the waveguide contribution, right? So even for constant N2 and delta, not a function of wavelength, just from the BV curve, this will be a non-zero number, right? Okay, so I hope these two contributions are clear, right? This is coming from the variation of the refractive index of the material with wavelength, and this is coming from the waveguiding effect itself. So even if the material index is constant with wavelength, this part, because the mode profile is changing with wavelength, right? That is contributing. Okay, so to calculate the total dispersion of any fiber, basically we calculate these individual contributions and then add them up together. So the first part, material is basically just a property of silica. Right, so if you look at the refractive index of silica, as a function of wavelength. Right, so you know it's about 1.45, right? But it's not exactly, and it varies a little bit with wavelength. So typically, the refractive index goes down with increasing wavelength. So this behavior is true for any material, right? Any natural material at all you pick up, and if you look at the refractive index with the wavelength, it always goes down with increasing wavelength. Okay, and basically, again, d was recall proportional to the second derivative of so the first material contribution was just this material refractive index, the derivative, second derivative, right? So the material is just SiO2. Right, so basically there is an inflection point around here. So from concave upward, it becomes like convex upwards, this curve. So basically the second derivative crosses 0 around this 1.3 micron wavelength. Okay, so if we look at d, if we take the second derivative, so this material dispersion here, so basically around here it crosses 0. Okay, so because there is also a negative sign here, minus lambda over c. So here basically the double derivative is positive, which means dm is negative. And then after 1.3 micron, it becomes positive. Right, so this is in picosecond per nanometer per kilometer. Okay, so this is, let's say, for pure silica. So this exact value is about 1.27 micron. The wavelength at which the material dispersion crosses 0. So you can sort of vary the profile a little bit by doping it with some other material. Like for example, we dope the core region to make the refractive index slightly different, right? So what you can do is, so for example, if you dope it with germania, you can shift this zero crossing point a little bit. So like you can go up to, let's say, 1.31 or something. So this is doped with 13% germania or germanium dioxide. Okay, but basically, yeah, typically it looks like this. Below like roughly 1.3, it's negative, or again, recall this is normal dispersion, and this is anomalous dispersion. Right, and recall the telecom wavelength range is roughly here, right? 1.3 to 1.6. So in that range, actually, the material dispersion is anomalous. So why is there? So the question is like here. So when we wrote down the material plus waveguide, in the first term we got something like this. So here this was the cladding index. The question is why not the core? Doesn't matter, right? You could have N1 here, doesn't matter. Basically both N1 and N2 are basically just the silica, right? Maybe one of them is slightly because of this doping. Right, so recall this N2 came somewhere because like we wrote as we started from B and then we we had something like this, right? And this we wrote as some n2 times delta. We could equivalently have written this as n1 times delta, because n1 and n2 are so close, right? And then if you wrote it like that, you probably get d square n1 by d like this. But anyway, n1 and n2 are just the glass refractive index, so doesn't matter if it's n1 or n2, right? It's just need to look at the glass refractive index profile. There might be, in the absolute refractive index value, there might be a slight difference because of the doping in the core on decline. Right. Yeah. So, yeah, I hope that's clear. Right. So this profile, right, N versus lambda typically is modeled by what is known as the Selmayr equation. You might have heard about these. So for any material, you can model the refractive index versus wavelength like this. So basically, like the equation looks something like this. So n square, you write 1 plus summation of some terms, which look like some constant times wavelength square divided by wavelength square minus some constant. Okay, so the Selmayr equation has this form, and m can be any number of terms. Typically, they're like 3 terms or 4 terms, right? And for every different material, this constants aj and lambda j would be different. So you can check out this website, refractive index.info. Okay, and it has basically a catalog of any material under the sky you can think of. You can select that material, it will plot for you this profile, it will give you this equation, it will also give you the dispersion. So do check that out. Right, so for glass, for example, there are some constants that you can also check out. So glass, just like for electronic materials, like silicon is sort of the most well-studied material. For optical applications, glass is like sort of the most well-studied material. Okay, so these constants, etc., are all well known to like 10, 12 decimal places. This profile is very well known, etc. Okay, so basically in this telecom wavelength range, right? So in, let's say, from 1.25 to 1.65 micron, which is our range of interest for optical communications, right? This dispersion curve here, we can sort of approximate well by this simple expression. Okay, so where lambda sub ZD is the zero dispersion wavelength. So for pure silica, as I said, that's about 1.27 micron. Okay, so you can see that the material dispersion would be zero at exactly the zero dispersion wavelength. And in this range, it is well modeled using this simple equation. Okay, so you can see it's sort of in the tens of picosecond per nanometer kilometer range for these ranges. Right, so for example, if you look at, so here, 1.55 micron, which is sort of the most popular or most widely used telecom wavelength, the material dispersion is about 20 positive picosecond per nanometer kilometer. Right, what does this mean? Like if you have a source which has a 1 nanometer bandwidth, right, some laser diode or something, and then you send it over 1 kilometer of fiber, then you'll get 20 picosecond of broadening in the pulse. Okay, so this material contribution will be there for any type of optical fiber, irrespective of the core size, the index difference, etc. Right? This is just coming from the glass material itself. And then the second contribution is the waveguiding, which depends on the actual fiber parameters like core size and index difference, etc. Right? Because it depends on this BV curve. So we'll see that how we can modify this dispersion curve using this waveguide dispersion in the next class. So by designing the fiber with the appropriate parameters, we can change this dispersion profile, right? So right now you can see this is not very ideal, right? Around 1.3, of course, it's crossing 0 or very small. But as you go higher, right? So even here, like these are pretty, by modern standards, these numbers can be limiting, right? Imagine like hundreds of kilometers of transmission and you want to go to tens or 100 gigabit per second, right? Right, that is limiting. Yeah, how we can modify the dispersion profile? So there are special fibers that one can design to sort of have designer dispersion profiles. So we look at that a little bit. The waveguide contribution in the next class. We'll end here for today. Lambda ZD is 0 total dispersion. No. So in this case, we only discuss material, right? So for this is only the 0 dispersion for the material. We haven't discussed waveguide dispersion yet. So right now this is just from the material. So you're right that so once we take the waveguide contribution into account, we can basically, so first thing will be that this 0 dispersion can be shifted, right? And also the profile can be changed. So we look at, so maybe if you want, you can call this CDM, 0 dispersion material.